I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
That's one small step for man, one giant leap for mankind.
Hi, I'm Jeff Plescia. I'm a planetary geologist at the Applied Physics Lab, which is part of the Johns Hopkins University. What I wanted to talk about here is the surface of the moon, what it looks like, and how it's come to be what we see it as today. This first image shows the surface of the moon as seen by the Lunar Reconnaissance Orbiter imaging system. It shows the front side on the left and the far side on the right. And what you can see in this image is that the moon is sort of divided into two kinds of terrain. A relatively dark area, which are called the mare. Those are areas of volcanic basalt. And the brighter areas, which are the cratered highlands, which are very old. The view we see of the moon today is a result of the way it formed. After the moon fissioned off from the Earth from an impact, it was very hot and molten. Slowly it cooled, and once it had a solid surface, then it was able to record impacts. And so during the late heavy bombardment, the end of accretion, the moon was bombarded by a number of giant impactors, which formed a series of very large basins, and then later the surface was covered by volcanics in the basin interiors. Those are the mare today. And over the last 3.5, 4 billion years, impacts have continued to form on the moon. And so it's the impacts that primarily shape what we see on the moon today. Volcanism is important, but only within the mare. And even there, the impacts continue to form and shape the surface. Looking at it in a map perspective, this image shows the moon as it might have looked 4 billion years ago or 4.5 billion years ago, after most of the basins had formed, but before the volcanism occurred in the mare. So the blue areas are basins interior, and in this case, the largest one is the Imbrium Basin. This image on the right now shows what the moon looks like today. The red areas represent areas of mare volcanism where basalt has filled in the low areas. And so we see this sort of dichotomy. The dark areas are basalt, relatively smooth at the large scale, and the highlands, which are bright, they're a north acidic feldspar, and they're very rough on a large scale. When we look at the topography, you can see the same thing. The image on the left shows the front side, and the sort of bluish greenish areas are the relatively smooth mare. On the right is the far side, which is dominated by the highlands, and you can see the topography is higher, and it's also much rougher. At the bottom of the image on the right-hand side is the South Pole Aitken Basin. This is the deepest elevations on the moon, and this represents one of the largest impact basins in the solar system. This is just a view from orbit, looking across the highlands in the bottom of the image and up towards the lunar mare on the top. The area on the smooth area on the top is where the Apollo 15 mission landed next to Hadley Rill. This shows a view across the lunar mare with the highlands in the background, and you can see that both the mare surfaces are darker and they're much smoother than the highlands. That smooth versus rough topography is really only relevant at large scales, kilometers, tens of kilometers, hundreds of kilometers. When you're actually walking around on the surface, the small scale topography is very much the same on both the highlands and the mare, and that's because you've had constant impacts going on over the last 3.5, 4 billion years, and it's roughed up the surface and made little craters and thrown rocks around. So this is the view at the Apollo 17 site, looking across the surface, and you can see some mountains in the background and to the left, and some large rocks in the foreground, and in between that is relatively smooth surface covered by regolith. This, on the other hand, is the mare surface at Apollo 12, and what you can see is there's basically nothing in the background. It's just a smooth, planar surface, but there are lots of little impacts scattered across the surface, and locally you'll find rocks around craters and things that have been dropped in by other impacts. So the surface of the moon is dominated largely by impact craters. The largest I noted before was the South Pole Aitken Basin, which is a giant impact basin on the far side, but craters range in the size from hundreds of kilometers down to a few kilometers, down to small millimeter-shaped features. The images show the Orientali Basin, which is on the limb of the moon, the crater Tycho and the crater Tsiolkovsky. In addition, there are small features too. This image shows a picture of one of the lunar samples that was returned, and right next to the yellow arrow you can see a little tiny pit. That's called a zap pit, and that was formed by a micrometeorite hitting this rock when it was sitting on the lunar surface and forming a tiny little crater. And finally, in this last image, you can see a single lunar grain, and it has a crater on it itself. This was formed by a very tiny little particle hitting this grain while it was sitting on the lunar surface and making a crater. We know cratering continues to occur at present. We can see occasional flashes from the Earth, and LRO, which is the Lunar Reconnaissance Orbiter, has taken multiple pictures of the same place over time, and what you can see in some cases is new craters have formed. And so in this set of images, you can see a before and after picture showing the formation of craters. These are relatively small, on the order of 10 or 20 meters across. The continual process of impact cratering over time has created what's called the lunar regolith, which is this fragmental layer that covers all the lunar surface. And this is formed by two processes. One is the impact abrasion and breaking up of rocks, and also by thermal stresses, but it's made up of a series of particles that range in size from tens to hundreds of meters across down to little tiny grains that are only a few microns. The surface, as I said, is dominated by impact cratering, and what that does is every time you form an impact crater, you deposit ejecta around the crater. And most of the ejecta extends away from the rim about the same distance as the diameter of the crater. So if you had a 1 kilometer crater, for example, the continuous ejecta would extend out about 1 kilometer from the rim, and so you'd have a circular area about 3 kilometers across that's covered by the crater and the ejecta. And this process happens over and over and over again over billions of years, and so you get this sort of pattern of individual craters forming here and there, with sometimes the ejecta overlaps, sometimes it doesn't. What this does is it generates a kind of stratigraphy on the moon. And the cross-section, if you will, shows two columns. One for the highlands, where it's composed of this very fine regolith surface that's about 10 or 12 meters thick on the surface. Below that is what's called the megaregolith, and this is all the debris from the basins that were formed during the first few 100 million years of the moon in existence. That slowly grades down into sort of competent rock crust. The other column shows what the cross-section might look like on the Mare. You have the same sort of fine-grained surface regolith that's only about 3 or 4 meters thick on average. Below that is the basalt from the lunar Mare fill. These are layers of basalt that were laid down over a few 100 million years after basin formation. Below that, you get into that same megaregolith basin deposit that sort of covers the whole moon, and eventually again that would grade down into a solid crust. The picture shows a cross-section across Hadley Rill, and in this rill is kind of an erosional feature formed by lava, and it's exposed the cross-section of the uppermost few meters of the crust. And what you see at the surface is the regolith, this fine-grained layer of debris that overlies competent basalt. The lower part of the outcrop it's a little unclear whether you're looking at regolith that has just simply fallen down from above and covered the slope, or whether that's actually a buried regolith layer that was formed and deposited before the lava flows. But there is this general stratigraphy within the Mare of debris over basalt, and in the highlands of regolith over the megaregolith. But when you look at it in detail, the Apollo mission took cores, and they dug a few trenches, and they took some other kind of measurements. And what it showed was that while at any given place as you dig down, you go through different layers, the layers are not laterally continuous very far, because essentially you've got this sort of pattern of individual craters putting down ejecta patterns around them. You get this overlapping sequence that don't extend very far. And so even at a given landing site, they look at different cores, and while there was layering in all the cores, you couldn't trace the layering from one core to the other. So it shows that while there's layering, it doesn't extend very far. And so if you were looking at a particular layer, it would extend for a few meters or a few tens of meters or maybe a kilometer, and then it would be replaced by another layer. The surface of the moon is littered with rocks. Most of them occur around fresh craters. This shows one of the craters at the Apollo 17 site. This crater is only about 20 meters across. It's at what was called Station 1. It was one of the places where they sampled. The crater, as you can see, there's rocks scattered around the rim. That's typically what happens. In the Mare, you excavate down into the basalt and you generate rocks around the craters. In the highlands, you generate rocks either because they were buried in the regolith or megaregolith primarily. There's no solid, competent basalt layer in the highlands to excavate, but there are rocks around fresh craters in the highlands. This is the Apollo 15 site showing Hadley Rill. What you can see is some layering in the walls. These are the basalt flows we talked about previously. But those basalt flows are sort of broken up, and what happens is the rocks weather out and roll down the hill and wind up on the bottom of the rill floor. So that's another way rocks get exposed at the surface. Finally, within the megaregolith, there are giant blocks. In the case of hillsides in the highlands or central peaks, some of these blocks roll down the hill and are found at the bottom of the slope. This first image shows the central peak area of Copernicus, and what you can see around the bottom of the massif are a bunch of boulders. The other set of images is from the Apollo 17 site, and again, the massifs are made up of this megaregolith, and this shows one of the boulders that was sampled at Station 6. You can see the boulder trail where the rock came out of the megaregolith, rolled down the slope, made a trail behind it, came to rest at the bottom of the slope, and you can also see the same rock image taken from the surface, which shows Jack Schmidt next to it for scale. And so this boulder is about 30 or 40 meters across, and it rolled down the hill and came to rest at the bottom of the hill. In addition, you can eject large blocks from some of the larger impact craters. This first image shows a boulder sitting up on the top of the central peak of the Tycho crater. This boulder is about 100 or 150 meters across, and it's just sitting there. So it was lofted up into the air and fell back down on the surface and came to rest. The other image shows a block in the ejecta. This block is about 300 meters across. This was ejected from the interior of the crater, thrown out, and came to rest out on the ejecta blanket surrounding the crater. The distribution of rocks is very inconsistent across the lunar surface. These are some observations made at the Apollo 16 site. One area is relatively old and has relatively few craters. The other area, which was up near North Ray Crater, has a lot more boulders on the surface. And that process, as I said, is largely due to the fact that you get boulders around fresh craters. And so depending upon the age of the area, you may be more or less craters. Now, we know that this complete surface of the moon is not covered with rocks, and so these rocks must go away. The process of erosion of rocks is two components. One is the sort of continuous abrasion by micrometeorites and larger fragments, and also by a process called thermal fatigue, which we'll talk about in a second. So once the rocks are exposed at the surface, they're slowly abraded over time, and the cartoon shows what it might take to how long a rock of a given size might last. And basically, in a few millions or tens of millions of years, most of the rocks are removed from the surface because of the effects of impact cratering and abrasion. And so when you see a crater with lots of rocks around it, you know it's relatively young because the rocks wouldn't be there if it was an old crater. The other process that occurs is occasionally you will actually hit a rock with a projectile big enough to break it. And so what this shows is a rock that rolled down the hill, is sitting at the base of the hill, and it's completely fragmented. And so one of the thoughts is that this was actually hit by a small projectile that had enough energy to simply disintegrate the rock and turn it into a pile of smaller rocks. In addition to being hit by large objects that can fracture a rock or break it up completely, the micrometeorites grind the rock down over time. And what this picture shows is from one of the rocks at the Apollo 14 site that's broken. What you can see in the picture is that there's a little sort of pile of debris, fine-grained debris, right around the bottom of the rock. And this is a result of continuous bombardment by micrometeorites dropping little grains off, and they pile up around the rock, and they make this little sort of apron around the rock. So this process of abrasion is one way in which rocks are slowly removed. The other process is what's called thermal fatigue. Any surface that sits out in the sun over the course of a day, even if you go out and touch your sidewalk, you know that it gets hot in the morning when it gets heated up by the sun, and at night it cools off. That process, occurring over and over and over again over billions of years, produce stresses, and those stresses will break up the rock over time and slowly disintegrate it as well. The problem is with this particular process is that it only works on a relatively large size object, centimeters or larger. The very finest scale material is essentially isothermal, and so you still need the gardening and the micrometeorite bombardment to grind stuff down into the tens or hundreds of microns, which make up the smallest size fraction of the regolith. But the process of impact is not just one way of breaking stuff down. It also makes stuff. At the finest sizes, when a micrometeorite hits the ground, it will melt some of the regolith, and when that regolith melt freezes, it will freeze together some of the particles that were there. And this shows agglutinates, which are these little particles that are made up of smaller particles melted together by glass due to a micrometeorite impact. So you're building up these little tiny particles that are on the order of a few hundred microns or maybe a millimeter or two across. These particles are really a problem for lunar exploration because they're very sharp, they're very angular, and they're very hard, and they tend to scratch stuff. And one of the things that happened on the Apollo missions was that if the dust got on the camera lens and they tried to wipe it off the wrong way, it scratched the surface. So this is something that needs to be considered in the future for lunar exploration. The bottom of craters, another kind of rock was found. These are called regolith breccias. And so you had loose material on the surface, you had an impact crater, there was enough heat and energy that it essentially fused together some of the materials that were there to make what were called instant rocks or regolith breccias. And these were sampled at a number of places during the Apollo mission. So you have sort of two competing processes. At the small scale, impacts are making particles, and at the large scale, they're breaking them down. The impacts also create craters, which we've talked about, and the frequency of craters varies quite a bit around the moon. On flat surfaces on the Mare, there are relatively few craters. On flat surfaces on the Highlands, because it's much older, there are a lot more craters. But one thing you will notice when you look at pictures of the Highlands is anytime there's a slope, there are very few craters there. And that's because the constant micrometeorite flux essentially just erodes these craters, and the regolith creeps down the hillside and reduces the number of craters that you see. So the number of craters varies both as a function of age. The older the surface, the more craters. And if there's a slope, you'll have very few craters despite the age of that surface. Another process of moving material around on the moon is mass wasting or landsliding. This image shows a view of the Apollo 17 site from orbit, and you can see the bright area extending off what's called the South Massif onto the valley floor. That's a landslide that came off the Massif. There's a couple of arguments about how that landslide formed. One is that just some seismic shaking may have loosened material and it flowed down the hillside and onto the valley floor. Another argument is that material from the Tycho crater, thousands of kilometers away, hit that surface and generated the landslide. We really don't understand which of the two processes occurred, but it did generate material that flowed down the surface and out across the valley floor. Another place where you see mass wasting and landsliding is in the interior of large craters. Loose material collects up near the rim, and occasionally, either because of an impact or a seismic event, it gets shaken loose and it rolls down the hillside to the crater floor. These images show a number of different examples where the stuff comes down in nice little linear lobes, and then eventually, if it's still moving when it hits the floor, it spreads out. You can tell they're moving along the surface because if they hit a topographic obstacle, they'll bend around it or something, or just stop. Particle sizes range from very large things that you can see in orbital images down to very fine-grained stuff, which we can't resolve with the Lunar Reconnaissance Orbiter cameras, which can resolve particles on the order of a half a meter or a meter. So there's a fairly large size range in the debris that's rolling down crater walls. The characteristics of the regolith, when you actually look at it in detail and take it apart, are fairly complex. This image shows a collection of a scoop sample, so everything that was scooped up was put in a sample bag and returned to the Earth. And when they were examined in detail, they found a couple of different kinds of materials, one of which were fragments of rocks and minerals, some of which were fairly large, on the order of a centimeter or so. And that size range goes from centimeters down to microns. At the smallest scale, usually what you have are just mineral fragments. And then there was a series of rounded little beads which turned out to be volcanic glass. of different composition depending upon whether they were at the Apollo 15 or the Apollo 17 site where these volcanic glasses were observed. So it's a complicated mixture of particles with a range of sizes and compositions and shapes. The size-frequency distribution of material is fairly complex. Most of the regolith is actually very, very fine, sort of a powdery, floury material where the average grain size is only 100 microns. So it's very, very tiny. There's a complete size range, though. I mean, as I said before, there are boulders hundreds of meters across sitting on the surface, which are really part of the regolith. But most of the material on a sort of mass or volumetric basis is very, very fine-grained. This has a tendency to make the stuff very adhesive because of electrostatic forces. So anything that touches the regolith essentially gets coated, and that stuff is very hard to get off. When you look at the pictures from the Apollo mission, the beginning of the EVAs, the suits were nice and white, and at the end of the EVAs, they were just filthy and completely covered with regolith, both because it adheres and also because all these little odd-shaped fragments stick very well to the fabric of the spacesuits. When you look at the sort of larger scale properties of regolith, the regolith gets very dense very quickly with depth. They had a hard time sticking even the flagpole into the surface because after a few centimeters, the regolith is very densely packed. This shows some examples from the different Apollo sites on what the regolith density looks like as a function of depth. The surface area is relatively low density, but it rapidly gets denser with depth. Depending upon what the layering is, you can see little changes in the regolith. Occasionally you get a low density layer sitting on top of a higher one, but in general it gets denser with depth. What these measurements show is that the density as a function of depth varies from place to place. And this echoes back to the fact that the individual layers don't extend very far. So in one place you'll go through one set of layers, in a different place you go through a different set of layers, and those layers will have different densities. Another way to look at the density in a sort of more larger scale is by looking at the temperature patterns on the surface of the moon. One of the instruments on the Lunar Reconnaissance Orbiter is a Diviner instrument, which measures the surface temperature. And what they found is if they look at the surface at night, the surface temperature varies from place to place. It doesn't cool off at the same rate everywhere at night. And what this turns out to be an indication of is a change in the density of the surface regolith. You can make models that show how the temperature will change as a function of time after the sun sets. This shows you something about the density of the regolith, and what we can see in these kind of data is that from place to place, the regolith density varies. Now, these measurements are fairly low resolution, and individual measurement is on the order of 300 or 400 meters across. So these are kind of showing average values of the density of the regolith from place to place. That compares to the Apollo measurements where you're looking at the density on the scale of a few centimeters from place to place. One other thing that was observed in these thermal data is that there are places around craters, fresh craters, young craters, that are very cold at night. They're colder than the surrounding area. And this is a real puzzle because it's not clear what process the ejecta could produce, what kind of properties it could induce, where the surface would cool off so very fast at night that the surface is actually colder than the surrounding. So this was discovered by LRO, but there's really not a good explanation for it other than to say, well, the regolith must be lower density, but how you lower that density in an ejecta blanket is not at all clear. The lunar regolith is also very, very cohesive. You can see the clear patterns of boot prints where the material is cohesive enough, it sticks together, and all the little subtle details of the shape of the boot print or shape of a rock that was sitting in the surface after it was removed are all echoed by the compressibility of the material. The softness of the material varies from place to place, depending upon whether it's been fluffed up by an impact or whether it's just been sitting there for a long period of time. What you can see in these images are boot prints. The astronaut has walked through an area of soft, low-density regolith, and so the boot prints are fairly deep, and then farther on, gone on to harder regolith, and you can see that the boot prints are relatively shallow. And so this is an issue also that's relevant to exploration, because when you get into these deep areas of soft regolith, you can bog down a rover. The lunar roving vehicle used by the Apollo astronauts got stuck in a couple of places, and the Lunokhod rovers, the old Soviet robotic rovers, also got stuck in a couple of cases because they got into very soft regolith. The stiffness of the regolith and the ability to sink in was examined by some experiments on Apollo. They used something called a cone penetrometer, which was just a little pointed rod, kind of like an arrow, that was pushed into the regolith, and the force it took to push the rod in was recorded. And so this shows some of those data. Again, depending upon where you are, the regolith can be easy to penetrate or hard in the shallow part, but at depth it's very, very hard. And on the early Apollo missions, when they tried to drill into the surface, it was very hard because the regolith was so densely compact, there was nowhere for that material to go, and they wound up getting the drill stems stuck in the regolith. The porosity of the very most upper surface, the upper few millimeters at most, varies from place to place. That's because there's what's called the fairy castle structure, where individual particles are just kind of leaning against each other, and there's a lot of open space. So there's a lot of porosity. In the case of the lunar surface, right at the actual uppermost surface, the porosity is 80 or 90%. There's very, very little material there, and it forms this very intricate structure. The impacts, like we said, break up stuff, and they overturn the surface over time. And so you get this continual process of an impact happening. It produces a pile of ejecta around the crater. Another crater hits nearby, digs up that ejecta and mixes it up. And so over time, the regolith gets mixed over and over again. Data from the Apollo cores, though, show that it's not a simple process. If you look down a core, the age of the material, the maturity of the material varies as you go down, which suggests that it doesn't happen in a way such that the surface is very well mixed and then very poorly mixed at the bottom. You get big events that deposit large amounts of material, and small events which deposit a small amount of material. And so this process forms a very complicated aging pattern as you look through the lunar regolith. One of the best ways to look at this was at the Apollo 17 site. One of the places they visited was Shorty Crater. This is where Jack Schmitt found the so-called orange soil, which was a volcanic deposit. He took a core there, and what it showed was that the upper 5 centimeters of the core was very well mixed, had very mature particles. Once you got below that 5 centimeters, though, the material was very immature and it hadn't been exposed to the surface and was poorly mixed. That crater is only 10 million years old, so what it shows is that the gardening rate, at least here at this time, after 10 million years, only the upper 5 centimeters has been mixed. And so one of the things we've been finding is that from place to place, the rate at which the material is overturned is very much dependent upon exactly what's happened at that particular location over the last tens or hundreds or billions of years. One of the issues that was observed on Apollo was this issue of dust. The finest fraction, as I said, coats everything, and this was a sort of operational problem. It coated the radiators on the rovers, so periodically they had to brush those off so it didn't overheat. It coated the lenses of the cameras and the suits, and so they had to clean stuff off. One of the particularly vexing issues was the fact that because it got everywhere, when they took the gloves off or took the helmets off from the suits when they got back into the lunar module, some of the dust got on those seals, and the next time they tried to put the gloves back on or the helmets back on, this grit was in the seals, and it scraped up some of the connections. And what was observed was that on the later EVAs, the suits lost a little bit more air than they normally would have, and that's because these seals really didn't stick as well as they would have at the beginning of the mission. And so this stuff is everywhere, and it's an issue for operations because, like I said, once it gets on something, it changes the thermal properties and it's very difficult to get off. The question about whether the stuff moves around on the surface has been an outstanding question since the Apollo program. Some pictures were taken from the robotic surveyor spacecraft before the humans landed on the moon, and at night they looked at the direction of the sunset and they saw this glow above the horizon. And it was seen on a number of occasions with different spacecraft, so we know it wasn't some photographic anomaly. And what it was suggested was that electrostatic forces on the lunar surface levitate the dust along the morning and evening terminators. And so what Surveyor was seeing was this dust that had been levitated off the surface and was levitated high enough that it could scatter sunlight after sunset, and it was observed by Surveyor. So this would suggest that material is being moved, at least levitated. On the other hand, one of the observations from the Apollo astronauts was that the rocks were clean. I mean, there might be some ejecta thrown on the occasional rock, but the rock surfaces themselves were not coated with dust. Similarly, the lunar retroreflectors have been there since 1969, continue to return laser reflections from the moon, so we know there's not deposition of dust, at least on human timescales, enough to cover the operational material, and we know from the observations of the rocks from the Apollo astronauts that there's not long-term deposition of dust. So exactly what's causing this phenomenon is not at all clear, and so it's one of the mysteries that just to be solved on the surface of the moon. The other experiment that was deployed during Apollo 17 that also indicated dust was moving around was this lunar ejecta and meteoritic experiment, the LEAM experiment. And as I said, like Surveyor, they saw a large increase in particles at the evening terminator just after sunset and just before sunrise. And so this also suggested there was particles moving around, but since nothing has coated the retroreflectors and nothing has coated the rocks, it may be that this material is just sort of moving up and down, and really you have the same grains just bouncing around as the terminator passes, rather than large amounts of material being deposited on the surface. We also know that the compositional and albedo features on the lunar surface are very sharp, and they've persisted for hundreds of millions or billions of years. So you know there's not a lot of material moving around sideways, but maybe there is material that just moves up and down periodically during the day. The poles of the moon represent a relatively unique environment. From a geologic perspective, they're not really any different than anywhere else on the moon. In the highlands, you've got lots of craters, it's relatively rough, but the poles of the moon only see the sun at a very low angle. And that doesn't change over the course of a lunar month or a lunar year. And so what happens is any place that you've got a deep crater at the poles of the moon, it's permanently shadowed. And these are some of the coldest places in the solar system. Temperature is only 40 or 50 degrees Kelvin. That's colder than Pluto is because they see no sunlight. The little bit of sunlight that does get scattered into it is not enough to change the temperature, but it is enough to allow an imaging system to take a long exposure picture and see into those areas of what are called permanent shadow. This shows one of those LROC, Lunar Reconnaissance Orbiter camera images taken with scattered light, and what you can see is the interior of the permanently shadowed craters is no different than any place else on the moon. There's material moving down the walls, the crater floors have material on them, there's ejecta scattered around. But because the temperature is so cold, what makes these craters interesting is they may be long-term traps for volatiles, hydrogen and oxygen in the form of water. And so in terms of returning to the moon, these are potentially sites of interest because if there is in fact a lot of water ice there that can be collected, that water ice can be melted, turned into water, can either be used for human consumption, or the hydrogen and oxygen can be used for fuel. And so the idea is that exploring these areas can facilitate future exploration of the moon or going on to some other body like an asteroid or Mars. One of the things that was observed during the landing of the Apollo mission that will affect future missions is that when you land, you disturb the surface. The rocket plume impinging upon the surface moves the dust, scours the dust, and there were dust clouds observed as they landed, which sort of hampered some of the visibility during the last few tens of meters of the descent. It really didn't have any problem here, but it does blow material around, and there is some concern that if you had a pre-existing vehicle or habitat nearby, that this dust could impinge upon those vehicles or buildings and cause some erosion. We know it happens, and so essentially what you have to do is land far enough away that you're not going to disturb the dust and propel it into something that's already on the surface. One of the things, though, that was observed by LRO is that there's, and it's probably a result of this landing plume impingement upon the surface, is you generate a bright spot around the lander, which is a little dark spot in the middle there, and this bright area extends out about 100 meters or so from the lander. It's obviously some sort of disturbance has occurred. Nothing is really visible on the surface, but something is going on. We know it's not just a function of humans being there, for example, because this shows one of the Soviet Lunokhod landers, and you can see the same bright spot around the landed vehicle, and you can see the rover tracks leaving the lander and departing the area. And again, once something touches that disturbed area, it makes it dark again. So we know there's some process that's disturbing the surface, but it's not clear exactly what. Presumably it's some fine-grained phenomenon that's occurring just in the uppermost layers, because as I said, other than directly underneath the lunar module, there really wasn't any obvious disturbance to the surface. Studying the moon is important for a lot of reasons. The moon has been often referred to as the witness plate of the solar system. The moon's been sitting there for 4.5 billion years. It's recorded all the different processes that occur. The nice thing about the moon is that it doesn't have an atmosphere and there's no liquid water on the surface, so there's no erosion. There's mechanical erosion from the impacts and thermal processes, but there's no chemical erosion. So when you pick up something on the moon, it's relatively pristine, so you can find rocks that date all the way back to the formation of the moon, and we can understand how the moon evolved. And so that provides us a view into the processes that have shaped all the terrestrial planets.